here's something I think is really cool. That R be some equation between x and y. And it is the case that for every x, there is a y such that that relates to x, right? So this is almost a function. R is almost a function because for every x, I can find a y, but there might be several y's. So it's not quite a function. And the question I have is when can we turn it into a function? Here's an example. Right, so that's a equals b plus c. For every a, I can definitely find some b and c that sum to a. But obviously there's a bunch of different choices. I don't know where I'm going with this. The first step is, my question is, assume, so first let's draw this graphically. This graphically is written like this. Given an arbitrary x, I have a y that relates to it. And assume this. What I want is to turn this into a function. So I want to find the function f such that f is included in R. So this, may or may not be true. Theorem, maybe? Who knows? So there's a bunch of things I want to say here. So first, let me go through an example. Here's my example. This is R. Here's this thing. And for every A, I can choose, tons of B and C to work. But, let's choose one. Can we choose one is the question. And the answer is, yeah, we can definitely make some choice. And the choice I will make will be this one. So I take A, I divide it by 2, and I copy it here and here. So that's B and C are the same, and they're equals to A over 2. This is a function from left to right. Given A, it chooses a B and C, and the inclusion here says that, if this is true, then for A, B, and C, then this is true. Obviously, it doesn't work the other way around. There's a bunch of other choices I could have made. I could have, actually, here's another interesting choice. I could have chosen B equals A and C equals 0. That's another valid choice. But here's a fact of interest. In the lands of graphical linear algebra, this is true. This is a theorem that whenever R always has, corresponding output for an input, then I can find a function under it. So this means, since in GLA all these functions are linear, it's like not only can I make a choice of y, I can make a linear choice of y, linear in x. So this is a pretty important theorem that you actually end up seeing in textbooks of linear algebra. But the reason I find this so interesting is that I can talk about it in a way that standard linear algebra cannot, because I can talk about R. I can talk about an equation that isn't a function, and it's one of my objects. But the way it works in normal linear algebra is that you don't really take equations as seriously as you do maps, matrices. So you can't quite, you will not write this. You will have to write in words things like, there exists a linear map that matches the thing. And this is one of the sort of subtle but drastic differences that I like about GLA, is this ability to talk about equations as the main object. And so here's, well, I mean, here it is. Here's a thing I can do. This is a theorem I can write, and it's fully symbolic. Well, not fully symbolic, but like it's fully in the realm of things I want to talk about. And it is true for linear algebra. It is also true for other things. It's true for piecewise linear algebra. I'm pretty sure it's true if you add multiplication as well. I'm pretty sure it's true for arbitrary equations between real numbers. Because then the normal choice theorem / axiom. Yeah. Why did I want to go with this? I don't really know, but here you go. Here's a theorem I can write. It's called choice.